Hello everyone, welcome back to A-Level Physics, Chapter 16, Circular Motion. And this is the chapter outline. So let's look into some example of object moving in a circle so that you can understand the application of this chapter better. Some example include a car moving in a roundabout, moon orbiting the Earth, a Ferris view at an amusement park, a satellite orbiting a planet. Now, to understand circular motion, we can look at just this clock. So the second hand of the clock complete one cycle in 60 seconds. And one cycle is 360 degrees. That's the amount of degree in a circle. It means that for each second, the hand moves 6 degrees. This example shows us that we can measure the motion of an object using angle and give us the idea of measuring the amount of rotation using angular displacement. So this is what angular displacement is. It's the angle which an object moves in a circle, and it is measured in radian. And how we can calculate that is simply to use the displacement here and divide it by the radius. Do note that angular displacement is just a ratio. So if the circle gets bigger, but it's using the same ratio, it will still result in the same angle. Now, just to sidetrack a little bit, there is also a way for you to convert radians to degree. You have already learned it in MF. So this is our angular displacement formula, S divided by R. So we know that in one circle, the circumference is 2 pi r. If we want to find out the amount of radian in one cycle, we can just use 2 pi r at the S column divided by r. We would have gotten that a complete circle consists of 2 pi radian. And 2 pi radian is equal to 360. That's the conversion we can do. If you want to find out how much 1 radian is equal to in angle, that's what you can do as well. Because 2 pi is equal to 6.284 equal to 360 degree. 1 radian is equal to this amount of degree. And if you want a simple formula, this is your formula. Now let's solve a work example. To convert 135 into radian, you can just use the formula I gave and you would have gotten the value in radian. But for most of the example given in the following, we're going to be using radian as our unit. Well, let's move on to this slide here. It says that when an object is traveling in a circle, its speed might be the same, but its velocity will keep changing because the direction is keep changing. Alright, so why does the velocity change? It's because the direction of motion of an object that's moving in circle is constantly changing. And the velocity vector is always tangential to the circle to that point. So the tangent is a straight line that touches the circle at a single point and is perpendicular to the radius. As the object moves along the circle, the direction of this tangent will keep changing. So if we were to draw a lot of tangents here, it should show you a circle. Now, we have talked about angular displacement. Now let's look into another term called angular speed. If angular displacement is the amount of distance an object rotates, angular speed is how fast it rotates. So the formula for angular displacement is this, and the formula for speed is this. We know that to find speed, we need distance divided by time. So that's why to find angular speed, we can just find out the change in angular displacement divided by the change in time. How much radian per second does the object rotate? And from this formula, you can also figure out the angular speed of a single revolution by replacing the change in displacement to 2 pi. So when you have 2 pi over t, that's the angular speed of an object in one revolution. So let's do a work example. A Pirelli wheel of an F1 car complete one single revolution in 0.5 seconds. What is its angular speed? So we could simply use 2 pi divided by 0.5, and that's how much it rotates. Right, talking about speed, there is a difference between angular speed and linear speed, which is the normal speed that we learned about. So linear speed is how fast an object moves along its circular path. Angular speed is how fast an object is rotating. So I'm just trying to give an example to show you the difference between angular speed and linear speed. So I have this diagram. All the runners are running at different lengths. Comparing the inner runner with the outer runner, the radius of the outer runner is greater. So the key concept is that the further a point is from the center of the circle, the faster its velocity, even if their angular speed remains. So the athlete running on the outer lane is actually the quickest if, let's say, they're all in the same line here, sync with each other. But we know that the linear speed of this runner is the fastest because the radius is the greatest. That's why we have another formula that can help you to find the linear speed of an object given the angular speed and the radius. So I have an example. 2 runners on a circular track. One runner is on the inner lane, and which has a radius of 50 meters, and the other runner is on the outer lane, which has a radius of 60 meters. Both runners complete one full lap in 60 seconds. Calculate the linear speed. So first of all, we have to figure out what is the angular speed. First of all, let's figure out the angular speed. Because they are running in one circle, we use 2 pi divided by 60 because both of them completed in 60 seconds. So that's the angular speed. But I want to figure out which one is faster. So in the inner lane, I could just use 50 multiplied by pi 30. 50 is the radius, which will give me this amount of speed. Whereas on the outer lane, as you can see, because the radius is bigger, it is actually running quicker. Now, having talked about angular displacement and angular speed, now let's move on to talking about the force involved in a circular motion. So speed is constant, but velocity changes due to direction change. Alright, a little bit of recap on Newton's first law. An object at rest will stay at rest unless acted upon by an external force. An object in motion will continue moving at a constant velocity unless acted upon by an external force. Now, imagine this car here moving in constant speed, but because its direction is always changing, there must be a force contributing to that. And this force is called centripetal force. It is always directed towards the center of the circle. Without centripetal force, the object would move in a straight line. Just imagine you are driving here and you don't turn your steering wheel. The car will just keep moving forward. For example, I have a fidget spinner. The force always has to be applied in the Ferris wheel. Also, the force is over here, solar system, and the sun is providing the gravity for the solar system. Now, the next part of the lecture, we're going to talk about acceleration. In circular motion, velocity changes constantly, and acceleration is the rate of velocity. That's why we want to study how to get the acceleration of the object, and this can be done using a vector diagram. So you just combine these little arrows here, and you will be able to find out the rate of change of velocity. So as you can see here from the resulting vector diagram, the acceleration is directed towards the center of the circle, and according to Newton's second law, acceleration is directly proportional to the net force. That's why the force is also directed towards the center. Now, at this point, you might ask, if the object is accelerating and changing direction, why is the speed constant? That is because force is perpendicular to the velocity. This force, the centripetal force, does not contribute to increment in speed. It only keeps the object moving in a circle. Of course, if you want to increase in speed, you can just step on the acceleration pedal better. And this is the formula for centripetal acceleration. A equal to v squared over r. A equal to angular speed squared times r. Let me just show you how to derive this formula. You will need to know that. So far, these are the formula that we have learned. Linear speed, angular speed. We have also looked at how we can derive the rate of change of velocity using a vector diagram. As you can see that the angle here is the same. That's why I can use the angular displacement formula here. I can just put the rate of change of v over v and rearrange the formula, let v move up. So I'm going to have v multiplied by the change in angular displacement, let both equation divided by the rate of change of time, and then simplify, and the acceleration. And once I simplify the equation first, I will find that A, acceleration, is equal to v times angular speed. We know that v is equal to wr, and therefore w is equal to v over r. So I just substitute the equation. A can also be v squared over r, and I could also change the v into wr, which will give me A equal to angular speed squared times r. So that's the two equations that you could use to calculate acceleration. Now lastly, we can also derive another formula for centripetal force. According to Newton's second law, is F equal to ma. We know that A is equal to w squared times r. We can just put this equation into A and we would have gotten the centripetal force formula. Now, having learned so many formulas, let's try to put it into examples. A car with a mass of 800 kg moving along a circular track of this amount. The car completes 5 revolutions in 2 minutes. Calculate the speed of the car. To calculate the speed, I need first the angular speed, which is 5 times 2 pi divided by 120, which will give me the angular speed. It's 5 because I'm completing 5 revolutions. Once you have the angular speed, just multiplied it by the radius, you will have gotten the speed of the car. Now calculate the centripetal acceleration. We can also use the formula that we have just learned. We just include the value that we calculated, square it, divided by 50, we would have gotten our acceleration. Lastly, centripetal force. Just use 800 multiplied by the acceleration we counted, and you would have gotten the centripetal force. So you can see these formulas, they are interrelated. The answer of one question often leads to another, so make sure you remember the formula well. Well, using what we have learned so far, we can also find out the orbital speed of a satellite. So we know that F equal to ma. We also know that A is equal to v squared over r. And Earth gravitational pull is W over mg. And A here, I can replace it with the velocity. And after some simplification, cancel out the m, fill it the value, this is the radius of the Earth, I would have found out the orbital speed of the satellite. And this is the speed to keep an object in orbit around Earth. It must travel at this speed. It continuously falls around the planet instead of hitting the ground, and gravity prevents it. But of course, we can't launch a satellite at this speed by ourselves. That's why we need a rocket. So now to give you more example on centripetal force. So look at this F1 car here. The car weight acts downward and the contact force acts upwards. And these forces are balanced. That's why the car doesn't fly, it doesn't act upward. And the friction force, the frictional force when the car turns toward the center, keeping the car in motion around the curve. And to keep the car moving in circle, that's when the frictional force comes in. That's when they brake, and that's why they can keep moving in a circle. Whereas the thing is a bit different on a bank road. When the normal force is tilted, it actually contributes to some of the centripetal force. What it means is that unlike a flat road where friction provides centripetal force, a bank road, the tilted normal force also plays a role. So if you are driving on a well-designed track, the car can actually turn well without relying too much on friction, increasing the cornering speed. But the angle is too low, additional force might be needed. Same goes to an airplane banking in the sky. When an airplane turns, it tilts its wing. The lift force from the wing has a horizontal component that provides the centripetal force, and the vertical component still balances the plane wave. So that's all of circular motion. You have learned a few more terms on how to solve the question like that. And thank you so much for watching. I shall see you in the next video. Goodbye.